Hello, my dear students. Welcome to the sixth lecture of electrostatic potential and capacitance. In this lecture, we will discuss the MCQ questions of capacitors and capacitance. So, the first question in this lecture: metallic sphere of radius r is charged to potential V, then charge Q is proportional to. So, here in this particular case, just consider that there is a metallic sphere whose radius is given r. And suppose if this metal sphere is having, or if it is given some charge, let it be q. Clear? So let it be positive charge. That means when we give some charge to it, that means these charges will distribute automatically on the surface of the given metallic sphere. Clear? And these will be distributed uniformly also. So here in this particular case, what will be the capacitance of this sphere? So we know that we know that there is a general formula, that means q is proportional to v. That means here in this particular case, q will be equal to c into v. Clear? So if that means the value of c will be equal to q upon v. Clear? So that means here in this particular case, what will be the potential of this metallic sphere if it is charged by q amounts? So in that particular case, potential will be nothing but kq upon radius of the given metallic sphere. So here in this particular case, it will be q divided by potential is nothing but kq divided by r. So q got cancelled out. So finally, how much we'll be getting? We'll be getting r upon k. Clear? So it will be nothing but 4 pi epsilon naught r. That means capacitance of a metallic sphere of a constant r will be nothing but 4 pi epsilon naught r. That means here in this particular case, always remember, if r is constant, then capacitance of the given metallic sphere will be constant. If we increase the value of r, then capacitance will increase. Clear? So this is one relation we are getting over here. So based upon that one, suppose if we'll be taking one example. What is the example over here? Suppose here in this particular case, assume that this metallic sphere is having some charge, that it will be 10 coulomb. Clear? And we don't know about the capacitance. We'll calculate that one. And suppose here it is asked that the potential of the given metallic sphere, if it is charged to 10 coulomb, then its potential will remains 10 volt. Clear? Then definitely by using this particular relation, q equal to cv, we can get the value of c will be q upon v, so it will be 1 farad. Clear? तो कैपेसिटेंस यहाँ पे हमें कितना मिलेगा 1 फैराड. तो यहाँ पे v मस्ट बी कांस्टेंट. ये यहाँ पे v को हम कांस्टेंट ले रहे हैं. क्लियर? दैट शुड नॉट चेंज. क्लियर? दैट इज फिक्स्ड. सो अभी इसमें हम क्या करेंगे, विल चेंज द वैल्यू ऑफ c. अभी हम c को अगर मान लो कि चेंज करें, लेट इट बी c प्राइम, एंड c प्राइम इज 2 फैराड. सो इफ इट इज 2 फैराड, देन व्हाट विल बी द चार्ज स्टोर ऑन द गिवन मेटेलिक स्फीयर. ये जो मेटेलिक स्फीयर है उसमें कितना चार्ज स्टोर होगा, तब जाके वहाँ पे पोटेंशियल हमारा वही 10 वोल्ट मेंटेन होगा. तो यहाँ पे पोटेंशियल तो हमारा फिक्स रखना है हमें, तो 10, इट शुड बी 10 वोल्ट. वी आर नॉट गोइंग टू चेंज द पोटेंशियल. दैट मीन्स हाउ मच चार्ज विल बी देयर टू मेंटेन दिस 10 वोल्ट पोटेंशियल. देन चार्ज स्टोर्ड विल बी नथिंग बट c प्राइम इंटू v. दैट मीन्स c इज 2 इंटू 10, सो दैट विल बी 20 कूलम. क्लियर? तो चार्ज वहाँ पे कितना स्टोर होगा, 20 कूलम का चार्ज स्टोर होगा. तो इसका मतलब ये है कि जब हम कैपेसिटेंस को इंक्रीज कर रहे हैं बाय कीपिंग द पोटेंशियल, देन इन दैट पर्टिकुलर केस चार्ज स्टोर्ड विल बी इंक्रीज्ड. क्लियर? पोटेंशियल को कांस्टेंट रखते हुए अगर हम कैपेसिटेंस को इंक्रीज करेंगे तो चार्ज क्या होगा, इंक्रीज होगा. क्लियर? तो ये रिलेशन. तो कैपेसिटेंस को अगर हम इंक्रीज कैसे करेंगे, तो कैपेसिटेंस को इंक्रीज कर सकते हैं बाय इंक्रीजिंग द रेडियस ऑफ द गिवन मेटेलिक स्फीयर. क्लियर? तो ये जो मेटेलिक स्फीयर है उसका रेडियस अगर हम यहाँ पे इंक्रीज करेंगे तो वहाँ पे कैपेसिटेंस का डेफिनेटली इंक्रीज होगा. क्लियर? तो इसका मतलब है कि जो चार्ज यहाँ पे स्टोर होगा, दैट यू कैन इंक्रीज और डिक्रीज बाय इंक्रीजिंग, इनडायरेक्टली बाय इंक्रीजिंग द वैल्यू ऑफ आर. तो आर को इंक्रीज करके हम यहाँ पे मतलब चार्ज स्टोर कितना होगा उसको हम चेंज कर सकते हैं. क्लियर? सिमिलरली इन द सेम केस इफ विल टेक अनदर एग्जाम्पल, मान लो कि हम दूसरा एग्जाम्पल हम लेंगे, तो उसमें हम क्या करेंगे, उसमें हम कैपेसिटेंस को कांस्टेंट रखेंगे. क्लियर? सो देयर इन दैट पर्टिकुलर केस एज्यूम दैट द चार्ज इज 10 कूलम. दैट मीन्स इनिशियली द चार्ज स्टोर्ड ऑन द मेटेलिक स्फीयर कितना है, यहाँ पे 10 कूलम है. क्लियर? और यहाँ पे जो केस है, मान लो कि हमारा कैपेसिटेंस हमें दे दिया गया है ऑलरेडी पहले से ही, इट शुड बी 1 फैरड। कैपेसिटेंस यहाँ पे कितना है, कैपेसिटेंस शुड बी 1 फैरड एंड वी आर फिक्सिंग दैट वन। यहाँ पे इसको हम कांस्टेंट कर रहे हैं, दैट विल नॉट चेंज। अच्छा, इसको कांस्टेंट कर रहे हैं, इसका मतलब क्या है कि ये जो गिवन रेडियस है, ये जो गिवन रेडियस वाला जो मेटेलिक स्फीयर है दैट शुड बी फिक्स्ड। यहाँ पे हम आर को चेंज नहीं कर सकते। क्लियर। अच्छा, तो कैपेसिटेंस यहाँ पे कांस्टेंट है, तो यहाँ पे पोटेंशियल कितना होगा? सो पोटेंशियल विल बी हमारे भी इक्वल टू क्यू बाई सी। क्लियर, भी इक्वल टू क्यू बाई सी, दैट मीन्स 10/1, दैट शुड बी इक्वल टू 10 वोल्ट। तो यहाँ पे पोटेंशियल हमें कितना मिलेगा उस मेटेलिक स्फीयर का, उसका हमें पोटेंशियल मिलेगा 10 वोल्ट। अब मान लो कि इस पर्टिकुलर केस में इसमें, क्लियर, इसमें हम 1 फैरड जो कैपेसिटेंस है उसको हम फिक्स करें, विल नॉट चेंज दैट वन, बट सपोज इफ विल चेंज द पोटेंशियल। क्लियर, अगर मान लो कि यहाँ पे हम पोटेंशियल को ही चेंज करेंगे, मान लो कि पोटेंशियल जो हम ले रहे हैं लेट इट बी 20 वोल्ट। क्लियर, मुझे यहाँ पे जो गिवन कैपेसिटर है उसका पोटेंशियल वहाँ पे इंक्रीज करना है। क्लियर, तो पोटेंशियल में वहाँ पे कैसे इंक्रीज करूँ? बाय कीपिंग कैपेसिटेंस कांस्टेंट। सो देयर इन दैट पर्टिकुलर केस हमें वहाँ पे क्या करना पड़ेगा? चार्ज को चेंज करना पड़ेगा। सो देयर इन दैट पर्टिकुलर केस व्हाट विल बी द चार्ज स्टोर, चार्ज न्यू चार्ज दैट विल बी प्रेजेंट ऑन द गिवन मेटेलिक स्फीयर विल बी इक्वल टू सी इंटू वी प्राइम। तो कैपेसिटेंस मेरा कितना है? 1 फैरड है ऑलरेडी, इंटू वी प्राइम इज 20, दैट मीन्स चार्ज स्टोर्ड विल बी हमारा 20 कूलम। क्लियर, तो चार्ज स्टोर कितना होगा? 20 कूलम, दैट मीन्स एज आई एम इंक्रीजिंग द पोटेंशियल, क्लियर, पोटेंशियल इंक्रीज हो रहा है, उसका मतलब है वहाँ पे चार्ज ज़्यादा स्टोर हुआ होगा। उसका मतलब ये है कि मान लो कि एक बॉडी यहाँ पे मेटेलिक बॉडी है और उसमें पहले से ही कुछ चार्जेस है। क्लियर, उसमें पहले से ही कुछ चार्जेस है और मान लो कि 10 कूलम का यहाँ पे एक चार्ज है उसमें। क्लियर, और हम यहाँ पे क्या करेंगे? एट इन्फिनिट में एक यूनिट पॉजिटिव चार्ज है, यूनिट पॉजिटिव चार्ज जिसको मान लो कि क्यू नॉट है, या फिर एक सिंगल पॉजिटिव चार्ज आप मान लो। assume that there is a single unit positive charge which is present at infinity, और उसको हम लेके यहाँ पे स्टोर करेंगे। क्लियर, तो जब हम उसको लेके यहाँ पे स्टोर करेंगे तो उसमें वर्क डन कुछ होगा, एंड दैट वर्क विल बी डन अगेंस्ट द इलेक्ट्रोस्टैटिक फोर्स ऑफ रिपल्सन ड्यू टू दिस पर्टिकुलर ऑब्जेक्ट। तो वो जो वर्क होगा दैट वर्क विल बी स्टोर्ड एज पोटेंशियल इन द गिवन सिस्टम। तो वो क्या होगा? इस सिस्टम में पोटेंशियल के फॉर्मेट में स्टोर होगा। मतलब जितना ज़्यादा हम चार्ज, ऐसे ही अगर हम बहुत सारे चार्जेस लेके जाएंगे तो ग्रेजुअली क्या होगा? ग्रेजुअली चार्ज स्टोर होगा, तो उसका मतलब है वहाँ पे पोटेंशियल डेफिनेटली इंक्रीज होगा। क्लियर, तो इसका मतलब है जो चार्ज स्टोर होगा दैट विल बी प्रोपोर्शनल टू वी, वो वी के ऊपर भी डिपेंडेंट है। क्लियर, सो हियर चार्ज इज प्रोपोर्शनल टू वी एंड आर, यहाँ पे वी एंड आर। और ये इसको आप कैसे लिख सकते हो? यहाँ पे अगर मैथमेटिकली यहाँ पे आप उसको शो करना है, दैट मीन्स हियर इन दिस पर्टिकुलर केस वी कैन राइट दैट हियर, यहाँ पे दैट मीन्स ओवर हियर Q will be equal to CV, and C is nothing but 4 pi epsilon naught R into V. So that means here this charge is proportional to both R and V. Clear, दोनों के ऊपर proportional है, that means it is proportional to both V and R. So option C will be the correct one for this particular question. Okay, here in question number 49, a spherical capacitor consists of two concentric spherical conductors. Two concentric spherical conductors, that means one spherical conductor that is the outer one is having radius r1, and inner spherical conductor is having radius r2, held in a position by suitable insulating support as shown in figure. The capacitance C of the spherical capacitor is. So here in this particular case it is asking us to find out the capacitance. Clear, so here in this particular case what is the formula to find out the capacitance? So formula to find out the capacitance is simply चार्ज स्टोर्ड ऑन आइदर ऑफ द प्लेट्स। क्लियर, जैसे कि हम नॉर्मली क्या करते हैं कि मान लो कि पैरेलल प्लेट कैपेसिटर में क्या होता है कि एक तो आपका पॉजिटिवली चार्ज होता है प्लेट और दूसरा आपका नेगेटिवली चार्ज प्लेट होता है। तो पॉजिटिव चार्ज Q, नेगेटिव चार्ज -Q। तो जब हम उसमें कैपेसिटेंस लिखते हैं, कैपेसिटेंस कैलकुलेट करते हैं C इक्वल टू Q/V, दैट मीन्स यू विल हैव टू टेक आइदर ऑफ द चार्ज। क्लियर, कोई भी चार्ज आपको लेना है। क्लियर, टोटल चार्ज, नेट चार्ज तो 0 होगा, बट हमें यहाँ पे कैपेसिटेंस जब भी हम निकालते हैं तो कोई भी एक चार्ज लेंगे और मैग्नीट्यूड वाइज दैट शुड बी पॉजिटिव। क्लियर, और V यहाँ पे क्या होगा, V इज द पोटेंशियल डिफरेंस बिटवीन द प्लेट्स ऑफ द कैपेसिटर एंड दैट पोटेंशियल डिफरेंस इज ऑल्सो टेकन एज पॉजिटिव। क्लियर, चार्ज भी यहाँ पे पॉजिटिव लिया जा रहा है और पोटेंशियल डिफरेंस भी हमें पॉजिटिव लेना है, क्योंकि हम हायर पोटेंशियल जो है पॉजिटिव वाला प्लेट, और इसको हम एज्यूम करते हैं, ये जो नेगेटिव वाला प्लेट है इसको लोअर पोटेंशियल एज्यूम करते हैं, तो पोटेंशियल डिफरेंस मीन्स हायर पोटेंशियल माइनस लोअर पोटेंशियल, सो दैट विल बी ऑलवेज पॉजिटिव। तो वैसा ही इस वाले पर्टिकुलर केस में जब हम स्पेरिकल यहाँ पे ये जो कंडक्टर्स यहाँ पे प्रोवाइड किया गया है, तो एक आपका जो आउटर वाला स्फीयर है उसका इनर वाला सरफेस है, दैट इनर सरफेस इज पॉजिटिवली चार्ज्ड एंड द इनर स्फेरिकल कंडक्टर जो है उसका आउटर सरफेस यहाँ पे नेगेटिवली चार्ज है। दैट मीन्स दिस विल राइट नाउ बिहेव एज ए स्पेरिकल कैपेसिटर। क्लियर, तो अगर ये स्पेरिकल कैपेसिटर की तरह बिहेव करा है तो आउटर स्फीयर में चार्ज है +Q एंड इनर स्फीयर का जो आउटर पोर्शन है, आउटर पार्ट है, आउटर सरफेस है, तो उसका चार्ज है -Q। दैट मीन्स चार्ज विल बी आइदर ऑफ द चार्ज मैग्नीट्यूड वाइज एंड पोटेंशियल डिफरेंस वी हैव टू टेक, लेट इट बी V। क्लियर, तो पोटेंशियल डिफरेंस मतलब वही हम लेंगे हायर पोटेंशियल वाला सरफेस माइनस लोअर पोटेंशियल। So here in this particular case, so first of all we'll find out the potentials of each spherical conductors. So the potential of the outer, what will the potential of the outer spherical conductor, ये जो है तो उसका पोटेंशियल क्या है। तो इसमें एक चीज़ हम ध्यान में रखना है कि दिस आउटर spherical conductor is earthed, this is earthed and जब इसको अर्थिंग किया जाता है तो उसका मतलब है उसका पोटेंशियल जनरली कितना होना चाहिए, पोटेंशियल शुड बी 0। क्लियर, कोई भी अगर कंडक्टर है, अगर मान लो कि वो चार्ज हुआ है पहले से ही, उसको जब आप अर्थिंग करते हो तो उसका नेट पोटेंशियल जनरली क्या होता है, 0 होता है। क्लियर, बिकॉज सरफेस ऑफ अर्थ इज जनरली कंसिडर्ड टू बी हैविंग 0 पोटेंशियल। अर्थ का जो सरफेस है वो उसका पोटेंशियल हम 0 एज्यूम करते हैं, तो उसके साथ अगर आप इसको कनेक्ट करोगे तो उसका पोटेंशियल भी वहाँ पे क्या होगा, 0 होगा। अच्छा, लेकिन हम इसको प्रूव भी कर सकते हैं कि 0 कैसे हो रहा है। तो इसमें हमें 2 कॉन्सेप्ट्स वहाँ पे यूज करना है। कॉन्सेप्ट्स क्या है यहाँ पे कि मान लो कि एक स्पेरिकल कंडक्टिंग बॉडी यहाँ पे और उसका मान लो उसमें कुछ चार्ज है, मान लो कि +Q। क्लियर, और उसका रेडियस मान लो कि R। क्लियर, देन व्हाट विल बी द पोटेंशियल ऑन द सरफेस के ऊपर जो है उसका पोटेंशियल कितना होगा, तो उसका पोटेंशियल होगा KQ/R। क्लियर, अच्छा, सरफेस अगर मान लो कि पूछा गया कि सेंटर पे पोटेंशियल कितना होगा, तो वही KQ/R होगा। अगर मान लो कि अंदर में किसी भी जगह पर यहाँ पे हो या यहाँ पे हो, किसी भी जगह पे अगर पोटेंशियल पूछा होगा तो वो भी कितना होगा, KQ/R। क्लियर, अच्छा, अगर हमें यहाँ पे ये बोला गया है कि पोटेंशियल एट एनी पॉइंट आउटसाइड, क्लियर, आउटसाइड मतलब यहाँ पे, क्लियर, एंड इट इज सिचुएटेड एट ए डिस्टेंस एज्यूम टू बी स्मॉल r। क्लियर, तो r डिस्टेंस पर आउटसाइड पोटेंशियल कितना होगा, पोटेंशियल आउटसाइड विल बी सिंपली KQ/स्मॉल r। दैट मीन्स लोकेशन ऑफ दैट पॉइंट वहाँ पे लेना है, सरफेस हो या फिर सरफेस के अंदर में कोई भी लोकेशन के लिए पोटेंशियल में हमें रेडियस ऑफ द गिवन स्फीयर लेना है। और लेकिन बाहर में जब हम पोटेंशियल निकालेंगे तो उस केस में हमें रेडियस, उस केस में हमें जो लोकेशन है, जो पॉइंट है, दैट वो पॉइंट का डिस्टेंस हमें वहाँ पे लेना है फ्रॉम द सेंटर। क्लियर, तो इतना ही कॉन्सेप्ट है। तो इस वाले केस में जब हम आउटर जो आपका जो आउटर स्फेरिकल कंडक्टर है उसका पोटेंशियल जब हम निकालेंगे तो पोटेंशियल किसके वजह से मिलेगा, एक तो यहाँ पे जो इनर सरफेस ऑफ द आउटर कंडक्टर है दैट इज पॉजिटिवली चार्ज, तो उसके वजह से हमें पोटेंशियल एक मिलेगा, ये पॉजिटिवली चार्ज कंडक्टर की वजह से। और ये जो नेगेटिवली चार्ज स्फेरिकल कंडक्टर है तो इसके वजह से भी हमें यहाँ पे स्पीयर का, ये जो इनर स्पीयर के बाहर में नेगेटिव चार्ज है उसके बाहर में हमें यहाँ पे पोटेंशियल मिल सकता है। क्लियर, तो अगर हम जो आउटर स्पीयर है दैट मीन्स जिसका इनर सरफेस पॉजिटिवली चार्ज है, तो पॉजिटिवली चार्ज +Q है, तो पॉजिटिवली चार्ज अगर है तो उसके वजह से पोटेंशियल कितना होगा, पोटेंशियल विल बी हाउ मच, सिंपली K+Q/, रेडियस। रेडियस यहाँ पे कितना है, आउटर स्फीयर का रेडियस है यहाँ पे लिया गया है R1। क्लियर, अच्छा, ये एक हो गया। दूसरा फैक्टर यहाँ पे क्या है कि जो नेगेटिवली चार्ज इनर स्फीयर है तो उसके वजह से हमें बाहर में कितना डिस्टेंस पर पोटेंशियल कैलकुलेट करना है, वही सेम एज द रेडियस ऑफ आउटर स्फीयर। क्लियर, तो R1 डिस्टेंस पर ही हमें निकालना है, तो उसका पोटेंशियल कितना होगा, K-Q डिस्टेंस ऑफ द लोकेशन और लोकेशन ऑफ द पॉइंट ये नेगेटिवली चार्ज स्फीयर के लिए ये जो लोकेशन दैट इज आउटसाइड ऑफ द गिवन सिस्टम, तो आउटसाइड है मतलब हमें रेडियस, हमें लोकेशन वही लेना है, डिस्टेंस ऑफ द मतलब ये वाला डिस्टेंस, एंड दैट इज सेम एज R1, वो कितना है R1 होगा, सो दैट विल बी R1, so that means these two will get cancel out, so finally you will get the potential of the outer sphere will be 0, that means जहाँ पे अगर यहाँ पे ध्यान में रखना है कि अगर R3 है तो उसका पोटेंशियल वहाँ पे क्या होगा 0 होगा। सिमिलरली व्हाट विल बी द पोटेंशियल ऑफ द इनर स्पेरिकल कंडक्टर, इनर वाला जो स्पेरिकल कंडक्टर है उसके सरफेस में पोटेंशियल मान लो कि हमें यहाँ पे निकालना है। क्लियर, ये वाला लोकेशन पर हमें मान लो कि पोटेंशियल निकालना है। तो एक तो नेगेटिवली चार्ज्ड स्पेरिकल कंडक्टर है उसके वजह से सरफेस पे होगा, तो नेगेटिवली चार्ज स्पेरिकल कंडक्टर के वजह से जो सरफेस पे होगा वो कितना होगा, सिंपली नेगेटिवली चार्ज है मतलब -KQ, तो सरफेस में उसका उसी इनर स्पेयर का सरफेस मतलब रेडियस कितना होगा, इट विल बी R2। क्लियर, एंड और सेकेंड केस, ये जो पॉजिटिवली चार्ज यहाँ पे जो स्पेरिकल कंडक्टर है उसके वजह से अंदर में किसी भी जगह पर पोटेंशियल कितना होगा, सिंपली KQ डिवाइडेड बाय रेडियस ऑफ दैट गिवन स्पेरिकल कंडक्टर, तो उसका रेडियस कितना होगा R1। क्लियर, तो ये हो गया हमारा पोटेंशियल ऑफ इनर स्पेरिकल कंडक्टर। क्लियर, okay, so finally what will be the potential difference, potential difference will be delta V, that will be indicated by V, so here that will be nothing but VO minus VI। क्लियर, तो आउटर स्फीयर से इनर स्फीयर को अगर हम सब्ट्रैक्ट करेंगे तो हमें क्या मिलेगा, पोटेंशियल डिफरेंस यहाँ पे मिलेगा, तो इसको अगर हम सब्ट्रैक्ट करेंगे तो दैट विल बी दैट विल बी KQ बाय R2 माइनस KQ बाय R1। क्लियर, तो ये इतना हमें मिल रहा है। क्लियर, तो इस वाले पर्टिकुलर केस में ये हमें पोटेंशियल मिला बिटवीन द प्लेट्स ऑफ स्पेरिकल कैपेसिटर्स। देन व्हाट विल बी द कैपेसिटेंस ऑफ द प्लेट्स, देन कैपेसिटेंस C इक्वल टू Q अपॉन V, and it should be Q upon V is how much, so here in this particular case if I take KQ common, so it will be 1 by R2 minus 1 by R1, so if I take LCM of this one, so it will be KQ into, it will be R2 R1, it will be R2 R1, so here it will be R1 minus R2। Clear, so finally if we'll put this value over here, so it will be KQ into R1 minus R2 all divided by R1 R2। Clear, so Q will get cancelled out, so finally it will be how much, R1 R2 whole divided by K into R1 minus R2। Clear, so this will be the capacitance of the given spherical capacitor, so if we will put the value of K over here, so it will be 4 pi epsilon naught R1 R2 whole divided by R1 minus R2। Clear, so finally what we got, C is equal to 4 pi epsilon naught R1 R2 divided by R1 minus R2, this is the capacitance of spherical capacitor। तो फाइनली विल चेक द ऑप्शन में हमें चेक करना है कि 4 पाई एप्स यहाँ पे A और 4 पाई एप्सिलॉन नॉट R1 R2 by R1 minus R2, that is correct, so here R2 minus R1, that is wrong, here it is wrong, here 4 pi epsilon naught is given in the denominator, that is also wrong, so option A will be the correct one। Next in question number 50, two charged conducting spheres of radii A and B are connected to each other by a wire. The ratio of electric field at the surfaces of two spheres is, suppose here we will be taking two conducting spheres, two charged they have already said that charged conducting spheres। Clear, so here we will be taking two charged conducting spheres of having different radii A and B। Clear, so radii are given, so let me take the copy of this figure, it will be helpful later। So here in this particular case, these two spheres, suppose these two spheres are having radii of this one is A and radius of this particular sphere is B। Clear, and initially suppose they are charged। Clear, initially they are having some charges Q1 and Q2। Clear, Okay, so what it is said, two charge radii connected to each other by wire. Clear? So connected. After connection, charges let it be. So here in this particular case, just assume that these are two spheres having radius A and B. So after some time, what we are doing? We are doing some connection over here. So that means after connection, the charges are Q1 and Q2. Clear? So when we are connecting two charged conducting spheres, that means what will happen after that? Clear? So means there will be a redistribution of charges. So initially suppose the charges are q1 prime and q2 prime. Clear? So finally after connecting, what will happen? The charges will change to q1 and q2. Assume. Clear? So why the charges is changed? Because they are connected. So if any sphere will be having any potential, suppose this one is having potential v1 and here it is having potential v2 initially. Clear? So after connecting, what will happen? Suppose any, that means here in this particular case radii b is let radii b is less than radius a. That means here potential v2 will be greater than v1. Clear? So that means flow of charges will take place from higher potential to lower potential. Till what? Till the potentials of both become same. Clear? दोनों का पोटेंशियल जब तक सेम ना हो तब तक वहाँ पे चार्जेस का फ्लो होगा, और फ्लो होने के बाद जो चार्जेस प्रेजेंट होगा यहाँ पे मान लेते हैं कि Q1 एंड Q2. क्लियर? तो अभी यहाँ पे पूछा गया है कि फाइंड आउट द इलेक्ट्रिक फील्ड एट द सरफेसेस ऑफ टू स्फीयर्स. क्लियर? So ratio of electric field. So here in this particular case, assume the electric field just outside the surface. Electric field just outside of this surface is E1, and electric field just outside of this surface is E2. Clear? So if it is the case, then ratio of electric field E1 upon E2, and that will be nothing but how much? So we know that if it is charged, that means it will be having some surface charge density. Let it be sigma 1, and this particular one will also be having some surface charge density. Let it be sigma 2. So we know that electric field just outside the surface of a conductor which is already charged or having surface charge density, then it will be sigma upon epsilon naught. So E1 will be equal to sigma 1 upon epsilon naught, and E2 will be equal to sigma 2 upon epsilon naught. So these two will get cancelled out, so it will be sigma 1 by sigma 2. Clear? But what is sigma 1 and sigma 2? We know that surface charge density is nothing but charge per unit area, that means charge stored divided by surface area of the given metallic sphere. So it is nothing but 4 pi radius. Clear? It is the general formula is 4 pi r square. So if we will be putting over here, so sigma 1, that means the first metallic sphere, first conducting sphere which is having radius a. So for that one, surface charge density sigma 1 will be equal to charge stored, that is q1 upon 4 pi a square, all divided by surface charge density of the second conducting sphere will be equal to q2 upon 4 pi b square. So 4 pi will get cancelled out. So finally over here the ratio of electric field, what will be getting, E1 upon E2 will be nothing but simply q1 upon q2 into b square upon a square. Clear? So this is what we will be getting the ratio of electric field, but it is not completely in terms of the ratio of radii. Clear? So in that particular case we have to once again find out the ratio of q1 and q2. So how can you find out the ratio of q1 and q2? So here if we just look at this figure here, potentials of both the sphere will remain constant. So if potentials of both the spheres are constant, then here in this particular case, what is here what will be the potential of this particular sphere? Clear? ये वाला जो sphere इसका potential कितना होगा? It will be nothing but k q1 divided by radius is a, and potential of this right sphere will be how much? K q2 divided by b. Clear? So k got cancelled. So that means what will be the value of q1 upon q2? So q1 upon q2 will be equal to a by b. So if we put this value over here, so we'll get the ratio of electric field E1 upon E2 equal to q1 upon q2 is a by b whole into b square upon a square. So these two will get cancelled out. So finally what will be getting? So b upon a. So ratio of electric field E1 upon E2 is nothing but B upon A. B is to A. So here B is to A is wrong, this B is B by A, so this is the correct one. So option B will be the correct one. Okay, here in question number 51, the magnitude of electric field E in the annular region of a charged cylindrical capacitor. Okay, so here what they are saying, electric field in the annular region of a charged cylindrical capacitor. So which one of the following will be correct? It's same throughout. It's higher near the outer cylinder than the near the inner cylinder. Where is h1 by r square, where r is distance from the axis, and where is h1 by r cube, where r is distance from the axis. So I think there must be one option we have to correct. Clear? Because I think here either we have to correct C or D. Okay, we'll check whether we have to correct or not. So here in this particular case, suppose here we are given a charged cylindrical capacitor. So here in this particular case, assume that this is a cylindrical capacitor and it looks like this. This is something like this. Okay, so here in this particular case, assume that the inner cylinder is positively charged, clear, and the outer cylinder is negatively charged, clear. So here the outer cylinder is negative charged and the inner cylinder is positively charged. So that means over here what we can say, the field will be from the negatively charged cylinder to the positively charged one, clear. That means from the inner cylindrical body or from the inner cylinder to the outer cylinder, clear. So this is how the electric field lines will be inside the given cylinder. So what it is asking, that field in the annular region means between it means this particular region, the region between the two cylinders. That means between the outer surface of the inner cylinder and the inner surface of the outer cylinder. ये जो रीजन है, ये जो डिस्टेंस है, ये है हमारा, दिस इज द एनुलर रीजन. This is the annular region, clear. So in this particular region, what about the electric field, whether it is constant or it will vary. So here in this particular case, how will you find out the electric field? So in that particular case, generally if we consider the inner cylinder one, clear, and suppose if it is positively charged and if it is having some linear charge density lambda, clear. So then at that particular case, what will be the electric field at a distance, at some distance r? So how will you find out the electric field at some distance r? So in that particular case, what we'll be doing, will be constructing a Gaussian surface, clear. Gaussian surface or Gaussian cylinder of what, of r radius, Gaussian cylinder of radius what, small r. So that means over that particular case, if we will be applying the Gauss law, the closed surface integral E bar dot ds bar, that will be equal to charge enclosed divided by epsilon naught. So here in this particular case, if we will assume the electric field at a distance r due to this linearly charged rod that to be constant, that means we can take it outside. So it will be E into closed surface integral ds, clear. Here dot product should be taken as that means here theta should be what, theta should be 0. Why? Because electric field due to this positive, this is a positively charged plate, clear. So that means due to that one, field will be outward, and similarly the you can say the surface area of the given cylindrical body, that will be also outward, clear. So that means here in this particular case, angle between them should be 0. So if it is 0, then E ds cos 0, so cos 0 is 1. So finally E surface in closed surface integral ds, so no need to put any vector over here, so it will be charge enclosed. So how much charge is enclosed by the Gaussian sphere? or Gaussian cylinder over here. Clear? So, or you can say Gaussian surface. So charge enclosed is nothing but lambda into length enclosed. So assuming the length of the given cylindrical body to be L, then it should be lambda into L enclosed, so divided by epsilon naught. So what is closed surface integral ds? That means it will tell us the total surface area of the Gaussian surface. So Gaussian surface का total surface area कितना होगा? अगर ये radius अगर हमारा r है, तो circumference that is 2 pi r into length, that will give us the total surface area. So E into 2 pi r equal to lambda L divided by epsilon naught. So L got cancelled. So finally electric field we are getting lambda by 2 pi epsilon naught r. So this is what we are getting the electric field at a distance r due to a charged cylindrical body. Clear? So similarly at this location, which might be situated at a distance r, then electric field will be lambda by 2 pi epsilon naught r. If we increase the distance from the inner cylinder towards the outer cylinder, then it means this r will increase. That means electric field will decrease. That means this electric field will be variable in between the plates of the cylindrical capacitor. So it is first option, it is saying it is same throughout, so that is wrong. It is not same. Clear? That means it is electric field is not constant. Electric field is constant in which case if you are taking one positive charge plate and another negative charge plate, that means if it is the case of parallel plate capacitor, then in that particular case electric field will be constant. Clear? So second option is higher near the outer cylinder than near the inner cylinder. Clear? Electric field will be higher. What is it saying? Near the outer cylinder, at this location electric field will be higher, and at this location electric field will be lower. So that is wrong. Why? Because as we increase the distance r, as we move from the inner cylinder towards the outer cylinder, this r will increase, so electric field will decrease. That means near the outer cylinder field should be small and near the inner cylinder field should be large. So that is also wrong. And varies as 1 by r square, so no inverse relation. That means here electric field is inversely proportional to r. Clear? No inverse square relation. That means this is also wrong. And varies as inverse q relation, so that is also not there, so this is also wrong. So here in this particular case I think we have to do the correction means here we'll be doing the correction of this particular one. So it should be 1 by r. Clear? It should be 1 by r, then that particular option might be correct. So it should be correct only when if it is 1 by r. Clear? So here as the options given in the book are also option C, so it should be 1 by r. Okay, so here in question number 52, a cylindrical capacitor has two coaxial cylinders of length 20 centimeter and radii 1.5 centimeter and 1.66 centimeter. The outer cylinder is earth and inner cylinder is given a charge of 4 microcoulomb. The capacitance of the system is. So here in this particular case, suppose if we will take coaxial cylinders, this is the inner cylinder and let this one be the outer cylinder. Okay, so here in this particular case, suppose that means here this is the inner one and this is the outer one. Okay, so here what it is saying is that the outer cylinder is earthed. Outer cylinder is earthed, and another part over here is, let us assume the inner cylinder is given a charge of 4 microcoulomb. So inner cylinder is given a charge of 4 microcoulomb, so it is positively charged. Inner cylinder is positively charged. That means due to induction the outer cylinder will be negatively charged. Here the outer cylinder will be negatively charged. Okay, so fine. So here in this particular case, that means the field will be from the inner cylinder to outer cylinder. Here in this particular case, the field will be from the inner cylinder to outer cylinder, like this. Clear? This is the direction of field. Okay, so here if it is the case, another information what is given, the length of the cylinder is 20 centimeters. So let L be the length of the cylinder, and radii. So remember over here the radii, that is very very important. This is let it be inner radius, and let this one be the outer radius. So let it be RO, and let this one be RI, inner radius. Clear? So this is how we are going to represent. So let me magnify the image over here. Okay, so this is all about, so that means inner radius we are taking, this is RI, inner radius is RI and outer radius is RO. Okay, so fine. So here in this particular case, radii are given. So finally what we'll be doing, we'll be finding out the capacitance of the system. Okay, so here in this particular case, so how will you find out the capacitance? So capacitance C will be equal to Q upon V, and V is the potential difference between the given cylinders. Clear? So inner cylinder and outer cylinder. So here in this particular case, if we assume the inner cylinder to be A, named as A, and outer cylinder to be named as B, that means this potential difference will be Q upon V is what? Potential difference. That means it will be VA minus VB. As VA, that means cylinder A is positively charged, so it is assumed to be having higher potential, and cylinder B is negatively charged, so it is assumed to be lower potential. And Q is the magnitude of either of the charge that is given over here. So that Q can also be written in terms of linear charge density, that should be equal to lambda into L divided by VA minus VB. Clear? So right now what we'll do, we'll try to find out this potential difference. We know that dV equal to simply E dot dr. Clear? So here in this particular case, if we want to find out the net potential difference, so we have to do the integration. Clear? So if we do integrate this one, so it will be negative of E dr. Clear? So that means what we'll be doing, we'll be moving against the field. So the field is from the inner cylinder to outer cylinder, but here what we'll be doing, we'll be moving against the field. Clear? If we move here in this particular case, if we move from the outer to the inner one. Clear? If we move from the outer to the inner one, that means we are moving against the field. Okay, that is correct. And why this negative sign is coming over here? Because as we are moving against the field, also another thing, this potential, as you are moving against the field, that means this potential will increase. Clear? But simultaneously that distance, that means this particular distance, that will decrease. So that means here in this particular case, this it is coming out to be EDR. That means as we move from the outer to the inner one, that means what will the limits taken over here? Limits will be from the outer to the inner one. Clear? From the outer radius to the inner radius. Okay, so here another question, what is the electric field? So just in the previous question we have already calculated the electric field, the formula, and that electric field in between, in the annular region of the cylindrical capacitor, how much we got to be simply 2k lambda by r. Clear? So this is the magnitude of electric field that we got in the annular region, and this electric field is not constant, it is variable. Clear? So it is inversely related to r. So finally if we put this value over here, so how much we'll be getting? So integration negative from outer radius to inner radius, E is 2k lambda divided by r dr. Clear? So finally if we take 2k lambda outside, so it will be 1 upon r dr. So from ro to ri. Clear? So then means the potential difference will be getting over here, so negative sign should be there. So here minus 2k lambda 1 upon r dr, so it will be log. So it will be log natural logarithm r. So limits will be from ro to ri. Clear? So here in this particular case we can also put the take the negative signs. If we take the negative sign inside, then here this limits will change in the integration, this limits will change. So we can change also in the later part. So 2k lambda, so it will be log natural logarithmic ri minus log or ln ro. So finally over here, so it will be 2k lambda l log ro minus log ri. So finally 2k lambda log ro upon ri. So this is what we are getting. So finally the potential difference between the plates here in this particular case, if we just look at this arrow, that means radius of the outer cylinder, that is that will be obviously greater than ri, radius of inner cylinder. That means this ratio will be positive, that will be greater than 1. That means log value for greater than 1 will be positive. So that means this potential difference is coming out to be positive. Clear? So okay, fine. If this is the case, then what is the capacitance over here? The capacitance C will be equal to Q by V. Q is lambda into length enclosed divided by V is what? V is this value, so that is 2k lambda log ro by ri. Clear? So lambda will get cancelled out. So finally how much we are getting? We are getting, if we put the value of k also, k is 1 by 4 pi epsilon naught. So 2 and 4, so it will be 1 by 2 pi epsilon naught. So it will be 2 pi epsilon naught into length of the given cylindrical capacitor divided by log ro divided by ri. So remember this particular formula. This is the capacitance of a cylindrical capacitor. So capacitance of cylindrical capacitor is 2 pi epsilon naught length of the capacitor divided by log ro by ri. Clear? So it is in the natural logarithmic form. So if we want to do the calculation, then in that particular case we have to write 2.303 log base 10 ro divided by ri. Clear? So finally if we put the values, so this is the formula we must remember. So every time we not do the derivations to find out the formula, so we have to remember this one. Okay, so if it is the case, then what is the capacitance? So we'll put all these values. 2 pi epsilon naught values we know. Length is given. Length is how much it is given? It is, I think, 20 centimeter. Okay, 20 centimeter. Length is 20 centimeter. That means 20 into 10 to the power minus 2 meter. And outer radius is 1.6 centimeter. So 1.6 into 10 to the power minus 2 meter. And inner radius is 1.5 centimeter. That means 1.5 into 10 to the power minus 2 meter. Okay, so all these values you have written. So everything okay, correct. So if we'll put these values, so we'll be getting 2 into 3.14 into epsilon naught is 8.85 into 10 to the power minus 12 into length is 20 into 10 to the power minus 2 all divided by will be 2.303 log base 10. Ro is 1.6 divided by 1.5. No need to write whole thing because these two will cancel out. So it will be 1.6 divided by 1.5. Clear? So that value, this particular value will be a little bit greater than 1 because log 1 will be 0. So it is greater than 1. That means we'll get some positive value. Clear? We'll get some positive value and that will be very, very small. Clear? So if that is very, very small, then in that particular case, we'll be writing over here. So it will be it will be 2 into 3.14, so approximately 8 will be 6.28 into 8.85, 10 to the minus 12 is there, into here we'll be writing this 20, so it is 2 into 10 to the minus 1, so it is 2 into 10 to the power minus 1 plus 12. Clear? This is minus 12, so 10 to the minus, so it will be 10 to the minus 13 all divided by 2 point, let it be 2.3 into this particular value, let it be 0 point something 0 3, assume to be 0.03, nearly equal to. Clear? So we can calculate this particular value by using the log tables, or in the exam some information might be given over there. So assume that it is 0.03. So over here, how much will you be getting? So approximately, if we take do some approximations. So here, if we'll do calculation, so it is 1.1 approximately. Okay, if it is 1.1, so 1.1 into 0.03. So finally, here if we take it to be 8.85, that means approximately take it 9, and here let it be 6, 6. Then assume it to be so let it be uh, average, all in all average, how much will be getting? Average to be 54 nearly into 10 to the power minus 3 whole divided by, so it is 1.1 into 3, so it will be 3.3 into 10 to the power here 10 to the power minus 13, 10 to the minus 13, here 10 to the minus 13, so it will be 10 to the minus 2. Clear? So approximately will be getting 54 divided by 3.3. So if it is 3, then it is 18. If it is 3, then it is 18. So approximately we'll get 17 point something. Approximately we'll get 17 point, let it be 17.23 something like that. Clear? So if it is like that, then it will be 10 to the minus 2 if it goes up to the numerator, so it will be 10 to the plus 2, so minus 13 plus 2, it will be 10 to the power minus 11, so it will be 10 to the power minus 11. Clear? So this is what will be getting the capacitance. So let us check the options. Okay, in the options, okay, we have to put that means we have to just write little bit, we have to arrange, so it will be 1.72 into 10 to the power minus 10, so this much farad. Clear? So 1.7 into 10 to the power minus 10, so 2.8, 4.2. Option C, 1.7 into 10 to the minus 10, this is coming correct, and rest this, all these are wrong. So here in this particular case, option C will be the correct answer.